We got a test on December 5th. December 3rd is going to be review. And then, oh, when's Thanksgiving?
Next week.
The 21st? Oh, no, we got class. No, thanks, Thursday. Yeah, good. Luckily, we're on Wednesday, so we got class.
Oh, man.
Good. Okay, so on the 28th, which is 7 days before your test, that's where we're going to have the extra credit day. We just do not have a lot of class lectures left. So does that at least look reasonable for the E to the U? If you haven't memorized yet, that should at least look familiar. I'm trying to get a handle on this complicated function e to the minus x squared. And the whole point of these power series are I can trade in the function for an infinitely long polynomial. Polynomials are easy to work with. That e to the minus x squared, even though it's easy to write, it's actually a very complicated function to work with. So what I can do is I can replace it by its infinitely long polynomial representation. And then, just anticipating a bit, you see that when I plug in x equals 0, the whole thing's going to be 0. So what we get, and this is why we spent all that time with infinite series at the beginning of this chapter, is the answer to this, the exact answer to this integral is what I get by adding these infinitely many numbers together. And if I just need an approximation, I can get away with just adding finitely many numbers together. Put the pieces together. The approximating to do decimal places is the same as saying error is smaller than what? 0. And this is a special type of series. What do we call this type of series? When it alternates between plus, minus, alternating series, aptly named. And then you remember the slogan for the error for an alternating series. So you only have to remember one phrase and then you can work out the details. So what's the slogan for the error of an alternating series? Perfect. First. So what I'm going to do, I'm just going to go through here. It's going to be too hard to do this algebraically. So I've never taught how to do this in my algebra class. So 0.33, that's too big. What am I trying to get down to? So I'm trying to find a term that's smaller than 1. 0.005. So this guy is 0.02. We go to the next one. This is 0.004. Yeah, yes. So there's the first term that's smaller than 0.005. So there's the first unused term. So that means if I add these three together, I'm going to get my approximation. So 2 decimal places, the answer is going to be 0.33, 0.12, minus 0.1, which makes it 0.23. Oh, right down. It's going to be 1 minus 1/3 is 2/3. 0.67 plus 0.1, make 0.77 minus 0.02 is 0.75. So 2 decimal places, that integral is 0.75. So we worked out the power series for e to the x. 1 plus x plus 1 over 2 factorial x squared and so on. And going back to the square root of 17 example. So if you ask an algebra student for x close to 0, what's e to the x? Approximately 1. So this is what the algebra students say. Is the calc 1 student? let's say that locally, is if I'm close to x equals 0, this line is close to the function, and that line, the tangent line, is x plus 1. Make a good argument is that the Calc 1 student forgot to take into account that the function actually curves. So the simplest curvy function that approximates e to the x is 1 plus x plus 1/2 x squared. So there's two things we can do. Is we can either look at this as an infinite sum, which exactly gives the value of the function, or we can chop it off after some initial point and get an approximation. The further out we go, the better the approximation is. So we give names to these. And the notation we use for this is T2 of x. Call this the second degree Taylor